Hey guys, Yosoy Bimbabob here, and I'm again delving into virtual machine madness. And to review, virtual machines are machines that the instruction set is correct, but the operating system is sort of being emulated. And so when you're running a virtual machine that's like running Windows 11, what the virtual machine is doing is it's mapping all the system calls from Windows 11s to appropriate system calls in Mac OS. Some virtual machines actually operate at a much more primitive level. They actually are running the full OS, and there's something above it called a hypervisor. And the hypervisor then controls which virtual machine is actually running. So if you remember from last time when we were running Cinebench, we got basically a 20% performance decrease when we ran it in Mac OS versus running it in a Windows 11 virtual machine. And the reason why I didn't run in a virtual machine of Mac OS on Mac OS was because Cinebench doesn't run in the virtual machine of Mac OS and Mac OS. And so I was forced to do it in Windows 11. So if you're running a program that doesn't do a whole lot of system calls, you should get exactly the same performance in the virtual machine that you get in the native machine. And so I'm attempting to do that now with this program that I'm displaying here. So what this program is, it's a sieve of Eratosthenes, and it attempts to find the prime numbers between 0 and a number that's set as a constant at the top, which right here is 1 billion. And basically I picked that number to give me something in the range of 10 seconds for a run through. And then the other thing this thing does, it then does the thing 100 times. It gets the average and it finds the standard deviation. And it's not important that this is the most efficient implementation of that algorithm. What's important is it's something that stays entirely in memory and doesn't do any system calls in the inner loops. It does some system calls to do printouts, but there's so little of that they don't affect the time at all. So here we're showing the results after 100 runs. It had an average run about 9.9 seconds, varied from 10.1 seconds to 8.89 seconds, and we'll discuss that later, what I think is happening. And if we take that average of 9.9 and multiply by 100, it gives us 16 and a half minutes. And I put a time around it, and you see that that total runtime is time. So now let's move over to a Linux machine and see what happened there. So this is the results of the Linux virtual machine, where the average was 10.35. It varied from 10.2 to 10.5, and so on average was 5% slower, which wasn't what I wanted. I wanted hardly any difference. But you notice that the standard deviation on this is a lot smaller than the previous run. And it has a lot, it has a lot smaller range of runs. And again, I'll talk about that later. So here we have the results for running under Windows 11 virtual machine, and we see that the average was 10.63, which is 7% slower than what was running natively on the Mac, compared to the 5% that was running natively in Linux. We see that the variation is tighter than it was on the Mac. You get with a standard deviation of 0.11. And so we have to ask ourselves, what the heck is going on? So let's go through a couple of theories of why performance can vary on an Apple Silicon device. We know that they have performance cores and they have efficiency cores. And so that's one of the first things that I checked, and you see this running in the background. And what we're looking at is basically a virtual machine of Mac OS running the program. And I have the activity monitor up twice, once inside the virtual machine and once outside the virtual machine. And then I'm watching the cores as the program runs. And the thing to understand is the first 4 bars are the efficiency cores and the last 12 bars are the performance cores. And I came to the conclusion after running this on all the virtual machines that my program was pretty much always running on the performance cores. So that leaves frequency modulation is the final thing that's affecting performance, which I actually got a strong hint on. So when I first wrote this program and was doing it, I had the stream up, I was looking at things, I had OBS open, I was doing a bunch of things at once, and I was getting a much better performance than I was getting when I decided to actually run the time. And basically what you want to do when you're doing a performance thing on a core is you want to basically turn off all the processes that you can turn off and only have the one active that you're trying to measure performance on. And when I did that, that's when I got this 9.9 second number, which was significantly slower than you see in this virtual machine where I'm running a bunch of stuff. I got OBS open, I actually have a stream open, and you see that I'm getting like as low as 6.1 seconds per iteration. And one of the main reasons I started doing time was I was thinking, well, maybe I was using this counter that was internal to C, and as it was hopping from processor to processor, which is what it's obviously doing by looking at the process monitor, maybe that time was getting messed up. And I determined, no, that's not getting messed up. The time basically shows identical if you take the average and multiply it by 100, and it almost gives you the identical time. And so what I've decided that's happening is basically when the process runs all by itself, for whatever reason, the OS doesn't recognize that as a high performance reason to do anything, and so it leaves the performance core's frequency low, doesn't crank it up to improve performance. But for some reason, when you start running things in the background, all of a sudden it decides, oh, I'm having to do a lot of stuff. I need to crank up performance on my performance cores by increasing the frequencies. And so it does that. So it leaves you with this strange behavior where if you're running a single thread process and you want to get better performance, start up a stream, watch multiple streams. The other thing that I determined is that when I get into this fast mode, it didn't really matter if I was running the program in the virtual machine of macOS or natively in macOS. It got the same performance, which is what I was expecting for a virtual machine. But this still begs the question, determining what is happening in Linux and Windows 11 when I'm running this program. And what I decided is, unlike the statement I made in the previous video where I said, oh, I don't think it's messing with the way that the OS changes frequency. No, I think it is. In the Windows 11 and Linux virtual machines, the processor speeds aren't getting varied. And so if we look at the low speeds on those, it's 10.2 for Linux and it's 10.36 for Windows 11. And I think that's probably the speed of the program runs at the lowest frequency of the performance core. So now we're going to get into the funkiness that I saw when I was running under the Windows 11 developer environment. So right now, look in the upper left-hand corner, you see this ARM native tools coming in prompt thingamabobber. So if you want to do something for command line, you have to pull up this special environment that has all the stuff set up properly to run it. And there's one that just is like native's tool command environment. It doesn't say anything. And so that's the one that it first popped up. And when I did that, I need to get back over here. When I did that, I actually discovered that what I was running was an x86 version of it, which I have here as x86.exe, which I'll run right now. And I almost knew immediately upon seeing the number that came up that, oh, I must be running under the emulator. And when the first number pops up, we'll see why. Because basically it's roughly twice what the performance that we saw natively was. And so I suspected almost immediately that I was running x86 code. See, it's 23. It'll settle down to 20 for the next couple of runs. And so I checked. I brought up the task manager, and sure enough, it was running as an x86 binary. But the other thing is I looked into their the command line options for CL, their tool that compiles C. And I saw that there were some optimizations that you could do. And the optimization that supposedly gave you the best optimization for running with performance was the /02, which is what this is. And we can see that there's actually a pretty significant speed up improvement when you add in this optimizer. So tick tock, tick tock, tick tock, we wait for this to happen. 15.22, but what it'll actually do is it'll settle down, I think, into like the 14 range if we let it go for a bit. So almost immediately upon discovering this and discovering that I actually had x86 binaries and not ARM binaries, I of course ran the ARM binary with the optimizer, which is this ARM 021, which I'll switch to and I'll run right now.
And you will notice that the compiler switches that tell the compiler to do all the things that make it the fastest when you're in ARM mode is actually significantly slower than just compiling it with no options, which is what the run that's showing at the top is doing, which is the average is 10.63. And these are guys that are running, like 14.6. But what's interesting about this is that when you optimize with the /O2 thing in the ARM compiler, it gives you almost identical performance as if you do that same switch when you're running code that's emulated. So I'm like, is Microsoft purposely slowing down the compiler to match the optimized x86 when they're running their ARM compiler? Could they possibly be doing that? Maybe. I mean, there are some legitimate reasons to do that. So a lot of times when you're running a program like a game or something like that, and you're trying to match performance and you're trying to match frame rate, if it runs too quick, it'll actually mess up the rendering of the program. So this may be actually on purpose, and there may be a legitimate reason for doing it.
So in summing up, what conclusions have we come to? Well, we've come to the conclusion that in virtual machines, programs that only sit in memory actually do run at the same speed as natively. And we saw that in the macOS virtual machine. And the other conclusion that we came to is if something is running slower than you used to on your Mac, just start streaming a video and it'll speed it right up. This is Yo Soy Bimba Bob saying, don't be like me, like and subscribe.